Hello, this is Jake Abbott. In this video, I'm going to be talking about the canonical decomposition of a state space formulation for the analysis of controllability and observability. And what we're talking about here is we're talking about our standard state space form. I'll be doing everything in continuous time domain, but all of the results hold for discrete also. So we have some system that looks like this, the same system we've been looking at through this entire course. And we've now learned about controllability and observability. So controllability is something we analyze for this pair AB, and it basically says, is it possible for us, in a very kind of lay simple description, controllability says, is it possible for us to make these states evolve in time as we want using our input B? And controllability answers that question. The question of observability looked at the pair AC, and it said, is it possible for us, just by watching the output Y and knowing what our input U was, is it possible for us to figure out what the states are? And this question of controllability and observability was asked as sort of a binary question, like, is it controllable, yes or no? So if the answer is yes, then you're done. But if the answer is no, you can actually do a little more analysis. So let's say your system, you look, you say, is it controllable? And you say no. So the thing we start asking next, and that's what we're talking about in this video, is if it's not controllable, are there parts of our system that are controllable? And we can actually start thinking about the parts of the system being uncontrollable. Are they well behaved, meaning are they unstable? And if they're not, maybe we're not, our situation isn't so bad, even though it's not fully controllable. So let's start looking at this in more detail now. So we've been talking about this controllability matrix in the past, and the controllability matrix we write with this script C, and we stack that by looking at B, AB, all the way up to A to the n-1 power times B. And the first thing we need to know is that controllability is not changed by equivalence transforms. And that sort of makes sense. Really, when you think about it, basically nothing is changed by equivalence transforms. All of our system properties, controllability, observability, stability, they don't change just by looking at different combinations of the states. So if you actually go through here, and we consider like a really straightforward transform, so we're going to consider some new transform, some new x tilde variable, which is equal to some p matrix times x, where p matrix is an invertible thing, so it forms an equivalence transform. Then we can make an equivalence transform that looks like a tilde equals p, a p inverse, and we get our b tilde, which looks like p times b, and we get our C tilde, which looks like our C times P inverse. And we've seen this kind of stuff before. And the D matrix, which is the matrix that directly maps the inputs to the outputs, are completely unaffected by equivalence transforms all the time. So we've seen this sort of thing before. And if you do this transform and plug in these values into our controllability matrix, what you get is your controllability matrix is just equal to P times, or I should say, I'm sorry, that sort of the new controllability matrix is equal to C times our old controllability matrix. And we can do something similar for the observability matrix, and we get something like the new observability matrix is the old observability matrix times P inverse. And the important thing to note here is that if you take any matrix, no matter what it is, and multiply it by an invertible square matrix, its rank is unaffected. So whatever the rank of this controllability matrix is, that's the same rank of the new controllability matrix. Same thing goes for observability. So we're not fundamentally changing our system, its controllability or observability, by doing an equivalence transform. So that being said, we're going to do an equivalence transform on our system that will convert our system into this new form, this new canonical form. And when you say canonical, it's not a word we use in English frequently. It's just a mathematical way to sort of say like a standard form, meaning a form that has some physical meaning. Basically what it means here is, this A matrix in general is just going to be some random bunch of numbers. But what canonical means is it means that if we look at our system right, if we look at it sort of from the right view and think about mapping our states to some new set of states like this, then there's gonna be one form that has a more like natural form and gives us more insight about the physics of the problem than all of the other forms, and that's this canonical form. And so we're going to do this transformation, and it turns out that if you actually, let's say, so we're dealing with problems now here where our controllability matrix, so let's say rank of our controllability matrix is equal to some number, let's say it's equal to m, but m is less than n. So A is an n by n matrix, and we have an n by 1 state vector. So we have some rank that's less than full rank. So our system, if we ask, is it controllable? The answer is no, it's not controllable. So the question is, where can we go from here? So what we're going to do is we're actually going to choose a transformation, and the textbook has the full proof of why this works, but we're going to choose a transformation. We're going to pack up this P matrix, and not actually the P matrix, but the P inverse matrix. We're going to pack that up with these vectors, Q1 all the way up to Q to the M, where this is my M, and then eventually we're going to go up to Q to the N, because it needs to have n columns, because P is an n by n matrix, but only the first m of those really matter. So, and the way we're going to choose these first m is we're going to choose any m linearly independent columns of C, and we know it has it. It's not going to have n, because if it had n linearly independent columns, then this matrix would be full rank, and it doesn't, because we said its rank is m is less than n. So we're going to take it can be the first m linearly independent columns, or really any m linearly independent columns. And then once we pack those up, then we finish off this P inverse matrix by just choosing more columns that make this matrix invertible. So we're going to create our P matrix like that, and if we do this and then perform this equivalence transform using that Q, or that P, then what we get is our system broken down in this new form, where we can think of our system sort of as being decomposed into two systems. So this is going to be our new state vector, and let me just kind of write this out a little bit. So there's this little script C here, and then dot script C with a bar. Let me just write this out, and then I'll talk about what I'm doing here. So a tilde, this should be bar tilde 0, and then there's just junk here. Let's just leave it called 1, 2. Okay, so, and then there's the Y matrix also has a new transformed form, but y equals cx plus du, but that's sort of unimportant for the discussion here. So what we've done now is, using that equivalence transformation, what we do is we actually break our state vector into first this new state vector, this new x tilde state vector, but this x tilde can actually be broken down further, and it can be broken down into a set of controllable states, which we have this subscript C, and then not controllable states, which we call overbar subscript C. And the overbar, we use that to mean not in the way that you would in sort of traditional mathematical logic. So if I want to say some variable is the opposite of another variable, so I have some variable A, I could talk about not A. So if A is 1, then not A is 0, that kind of thing. So these are our controllable states, and these are our uncontrollable states. And as we start looking at this form always happens. So you'll always get a set of zeros here. And let's say you have 3 controllable states. Then this matrix, this upper left matrix, is a 3 by 3 thing. And let's say you have 2 uncontrollable states. Then this lower right is a 2 by 2 thing. And then you're going to get some numbers up here which are kind of unimportant, so we just call them A1, 2 because they're in the 1, 2 spot in this matrix. And these numbers could sort of be anything, including zeros. It's not like there has to be non-zero numbers here, but there's just junk there and we're not really going to care about it so much. But as you start looking at this, you say, look at where my input U can influence these states, and you realize your input can only influence the controllable states. And you've got this subsystem down here which we could rewrite essentially as x dot not controllable is equal to A not controllable times x not controllable. So we have this system which is just a homogeneous equation. There's no input here. So we have these states, these uncontrollable states, and the equations that describe them are these really simple set of equations. And there's no way our inputs can influence these states. So then the question becomes, is this system stable or unstable? If this system is unstable, so basically we're looking at the eigenvalues just of this one submatrix here. If this system is unstable, then if there's any initial state here, that initial state will grow to infinity and there's nothing we can do about it. So basically at that point you say not only is this system uncontrollable, but it's unstable and there's no way we can stabilize it. So this is the point where you would go back to the drawing board and say we have to add more actuators. We have to make U be able to influence these states. But let's say you look at this submatrix A of not C and you find out that it's stable. Then that means that whatever this initial state is in our X not C, so our uncontrollable states, whatever that initial state is, that's going to decay away to zero over time. And by looking at the eigenvalues of that matrix, you can see how fast they're going to decay away. So you don't have the ability to control them, but whatever they're going to do, after some period of time, they're going to decay away and they won't bother you anymore. So if you have a system that is uncontrollable, but when you break it down in this canonical decomposition and the uncontrollable states, you find that they're stable, this actually is still a decent system potentially. It's not controllable and you don't really need to make it controllable because the uncontrollable states, whatever they are, they'll eventually go away after some period of time that you can predict, and then after that your system behaves just like the way you want it to behave. And so this is the first result of this canonical decomposition. It turns out that there is a similar result for observability, and we can structure our P matrix a little bit differently. In this case, what we're going to do is we're going to look at the rank of our observability matrix, and that's going to equal some number m, and I'm using m again even though this is a different m than before, but it's some number m and it's less than full rank. And so in this case, the way that we're going to structure this matrix is we're actually going to build our in our P matrix. Let me see, I'm just looking at my notes here. So we're going to build our P matrix up so we've looked at this matrix here. Let's first write out what O is. So I have C times A, and that's going to go all the way down to C A to the n minus 1 in general. And if this were full rank, then I could pick, I would definitely have n different rows and columns that I could pick that would be linearly independent, but my rank isn't n, it's only m, so I'm only going to have m linearly independent rows and columns. So what we're going to do is we're going to build our P matrix now as this P1, which is a row vector, all the way down to Pm, where these these m rows are any m rows that are linearly independent of O, and there will exist exactly m. And there can be different combinations that you pick there, but you have to pick them. And then once you're done with those, then you just fill out the rest down to n, so that this is an n by n thing, to make P invertible. So you just pick those remaining rows to be linearly independent of the first m. And once you pick that P and do the same equivalence transformation that we had defined in the first slide, you're going to get this new system in which we have our new state vector that we can think of being broken down as an observable part and a not observable part. And so let me write that out. So I have my observable part and my not observable part. And then there's going to be sort of an observable B and a not observable B. And so this A matrix is going to always take this same form. There's going to be an observable A part here. There's going to be a not observable A part here. There's always going to be zeros here. And then you're going to get some numbers down here, which could be non-zero, they could be zeros. They're just a bunch of numbers and they're not super important, so we'll just call them spot A21. And then our Y vector, we have this new C matrix, and that C matrix is always going to have the form of this C here, which we call the observable C. And then you're always going to get a bunch of zeros here. State vector is the same. So we have our observable states and our not observable states. And then our D is just completely unaffected. So now we have this system. We did a different transformation than we did before, and so we got a slightly different form. But in this form, what we see is that our C matrix now is broken down very clearly, where there are certain states, which we call the observable states, that can be seen in our output Y, and there's another set of states, which we call our unobservable states, that cannot be seen in our output Y. And in this case now, in general, we have three different quadrants of our A matrix that in general don't have to be zeros. They can be zeros, but if you start looking at the A and B matrices here, they don't really tell you much information. I mean, U has the potential to influence both, in general, the observable states and the unobservable states. Now, in practice, there could be zeros in some of these entries here, and if they are, that would indicate not only is your system not observable, but it's also not controllable. But in this canonical decomposition, it really just breaks down your states into what can be seen in your outputs and what can't be seen in your outputs. So it's possible you can begin with either of these decompositions. So you could start with the controllability canonical form, or you could start with this observability canonical form. And if once you've broken it down like this, you can then take each subsystem. So in this case, I could take the observable subsystem, and I could break that system down using the controllability canonical decomposition. And then I could take this unobservable system and break that down using the controllable canonical decomposition. Or I can start the whole process with the controllable one and then do the observability decomposition on both. And the result will give you the same thing no matter what. The result will be we can take any system and we can break it down into 4 subcomponents. So our state vector now, we're going to have this big state matrix. And the states that we're going to have is we're going to have states that are both controllable and observable. We're going to have states that are controllable but unobservable. We're going to have states that are not controllable but they are observable. And we're going to have states that are neither controllable nor observable. And so this result will be the time derivatives of these same things. So controllable but not observable, the time derivative of not controllable but observable, and the time derivative of not controllable nor observable. And then we're going to have a B matrix that maps our input U. And when we break our big A tilde matrix down using this sort of 4x4 decomposition that we have, we're going to have one A matrix here, which corresponds to being controllable and observable. We're going to always get zeros in this position. We're going to get a bunch of numbers here that aren't super important, so we'll call that position 1, 3. There could be zeros there, there could be non-zeros, it's just numbers, and then we'll always get zeros here. Then we're We're going to get a bunch of numbers here that aren't super important. We'll call that position 2, 1. Then we're going to get an A matrix here, which corresponds to the A matrix of our states that are controllable but not observable. Then we're going to get a bunch of numbers here that turn out not to be super important, and we call that A2, 3, and then another bunch of numbers here, maybe zeros, maybe not. We'll call that position A2, 4. Then we'll always get zeros here, 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 and here. It just works out that you'll always get zeros there, and you'll always get zeros in this position as well. We call this matrix here the A matrix for the not controllable but observable part. We call this the A matrix for the neither controllable nor observable part. And then we get another bunch of numbers that don't really matter, and we'll call that just A of position 4, 3. So your A matrix is always going to break down like this, and your B matrix always breaks down to have zeros in these two bottom spots. And then we have a B matrix for our controllable and observable part, and we have our B matrix for our controllable but not observable. And you could say, well, why don't we have a B matrix for our uncontrollable parts? And that's kind of the beauty of this decomposition, is it kind of acknowledges that states that are controllable are the ones that U passes through B and can affect. And so in some ways, when you think about it, you go, oh yeah, my input should only influence a controllable part. It shouldn't influence the uncontrollable part, because if it did, then they'd be controllable. So that's why it breaks down like this. And then we're going to be able to break down our C matrix, and I'm not going to rewrite the state vector. It's the same exact state vector from above. And when we break down that state vector, we're going to say I'm going to have some C component that is both for the controllable and observable part. I'm going to get zeros in this entry, and I'm going to get zeros in this entry every time. And then I'm going to have a C matrix that's for the uncontrollable yet observable part. And the same sort of logic goes here. You only get components for the observable parts. You can be observable and not controllable, or observable and controllable, but the fact is only the observable parts come through in Y. The unobservable parts, the unobservable states, just don't come through Y at all, and that's the definition of what controllable and observability mean. So this is our big controllable decomposition, and it turns out when you look at the transfer function of our system, if we look at the transfer function of our system, we write that as C times Si minus A inverse times B plus D. It turns out this will be the exact same thing as if I only look at the C of the controllable and observable part. So I'm talking about just this one little submatrix here. Si minus A controllable and observable. So just this one little submatrix here, inverse, times B controllable and observable. So just this one little submatrix here. And then the D comes straight through. This is my transfer function. And so out of all of this information, all of this stuff in the A matrix, all of this stuff in the B, all of this stuff in the C, what it comes down to is only the controllable and observable parts appear in the transfer function. If it's not controllable, it doesn't appear, and if it's not observable, it doesn't appear. And so the way we can sort of think about why that would work is we can think about this sort of breakdown decomposition where you say, I have a controllable and an observable part. And what I'm saying is somehow the transfer function from U to Y only depends on that one little part. There's this other part that is controllable, but it's not observable. And my input U affects it because it's controllable. But whatever signal's coming out of there, I don't see it in my output because it's not observable. Then I have this other part of my system that is not controllable, but it's observable. And since it's observable, I can see it in my output Y. But I don't have any ability to affect what the states do in there because it's not controllable. And there's this fourth component of my system that's neither controllable nor observable. It's not observable, so I don't see it in my output. It's not controllable, so I can't attack it with my input. And so I have these sort of four different components of my system, and only this one little component actually matters in the output y. So the reason why that you can only affect these two is pretty obvious. Only sort of these states can be affected by you, but I can't see them. So I am moving them around, I just can't see them in my output y. And then I have these states that I'm moving and I can see. I think the question that's maybe a little not quite so obvious is why doesn't this matter? The part that's not controllable yet observable. Why don't I see that in the transfer function? And the reason I don't see that in the transfer function is fundamental to transfer functions is this idea that the initial conditions are equal to 0. Whenever I talk about transfer functions, that assumption is built right into the conversation. And if you think about it, this section here, it's not controllable, but if the initial states are 0, then this vector coming into this is just 0, and so I'll never see this uncontrollable part in my output y. If my initial states were non-zero, I would see this thing and I would see it evolving in time, and I would actually be able to observe it in my output y, but the transfer function doesn't allow for me to ever have non-zero initial conditions, so I'll never see this component. And so the last thing I want to say is that last matrix about the decomposition that was the 4x4 decomposition for controllability and observability. That matrix, while in that form it was a 4x4 matrix, don't be confused and think that that's somehow a bigger matrix. It's the same A matrix, it's the same dimension. They're all n by n. And so, if you find out, let's say you do the canonical decomposition for observability. And when you do that, you say, okay, I'm going to have some state that's observable. And let's imagine this is like a 3x1 thing. And then you have some decomposition that's not observable. And let's say this was a 2x1 thing. And so this whole thing assumes your original A was a 5x5 thing, and your original state vector was a 5x1 thing. So you do this transformation, this equivalence transformation, and when you're done, you say, okay, I can actually break my state down into a 3x1 state that's observable and a 2x1 state that's not observable. Well, later when you you further break it down and you say, I'm going to look at my state that is controllable and observable, and then I'm going to look at my state that is not controllable yet observable. This should be an overbar here. Not controllable yet observable. These two things constitute the entire observable matrix. So if I found out that my observable states were 3x1, then I further break that down into the observable and controllable, or observable and not controllable. So let's say this comes out to be a 2x1, then this thing has to be a 1x1, because there are exactly 3 states that are observable, and I'm further breaking them down. And then let's say I came over here and I said, okay, now I know my not observable states are 2x1, so I have to further break that down into, I can be controllable and not observable, and I can be not controllable and not observable. And so let's say you came across here and you said this was a 2x1 thing. Well, that would mean this is a 0x1 thing, because if this is 2x1 and this is 2x1, then there can't be any left. And so you can actually get this result where you say, I don't have any states that are not controllable nor observable. And so you do have to think about, breaking these systems down into smaller and smaller chunks, and it's okay if some of those chunks have 0 dimension. So, and that goes for everything we've talked about today. It's not like those matrices that are in general little square matrices. A 0x0 matrix is one of the options, so it's not like you always have to have every single one of those entries in all of those matrices.